Black holes, some of the most mysterious objects in the universe, come in different types, differing primarily in size and mass. These cosmic objects can be divided into three main categories: stellar mass black holes, supermassive black holes, and intermediate mass black holes, each with their own formation processes and characteristics. Stellar mass black holes are the most common type and are formed from the remnants of massive stars. When a star with a mass about 25 times that of our Sun exhausts its nuclear fuel, it undergoes a supernova explosion. The remaining core can collapse under its own gravity and become a point of infinite density, known as a singularity, surrounded by an event horizon beyond which nothing can escape. These black holes typically have masses ranging from a few to tens of solar masses and are scattered throughout galaxies, including our Milky Way. The supermassive black holes found at the centers of most galaxies are very different entities, with masses ranging from hundreds of thousands to billions of solar masses. Their origin is the subject of ongoing research and debate, but there are several theories. According to one hypothesis, they are formed by the merger of many small black holes and massive stars in the dense central regions of young galaxies. According to another theory, they may have formed as a direct result of the direct collapse of the massive gas clouds of the early universe. Over time, these mysterious giants grow, absorbing matter from their surroundings and merging with other black holes to become the colossal structures that hold galaxies together. Intermediate mass black holes, occupying the size range between stellar mass and supermassive black holes, remain somewhat elusive and less well studied. These black holes are thought to form from the merger of stellar mass black holes in dense star clusters or from the direct collapse of very massive stars in low metallicity environments. Their masses range from hundreds to thousands of solar masses, and they may represent an evolutionary bridge between stellar mass black holes and supermassive black holes. Although confirmed examples of intermediate mass black holes are few, they provide important clues about the scaling and growth processes that lead to the formation of supermassive black holes. Each type of black hole opens a unique window into the fundamental processes of the universe, allowing us to understand the evolution of stars, the formation of galaxies, and the mysterious nature of gravity itself. The mechanisms of their formation, while varied and complex, emphasize a dynamic and ever-changing cosmos that continues to fascinate scientists and enthusiasts alike. Black holes warp space-time through the profound effects of their enormous gravitational fields, a concept derived from Albert Einstein's general theory of relativity. This theory, formulated in the early 20th century, revolutionized our understanding of gravity by showing that massive objects cause the very fabric of space-time to warp. A black hole with strong gravitational attraction represents one of the most extreme examples of this phenomenon. Imagine space-time as a two-dimensional rubber sheet. If you place a massive object, such as a star, on this sheet, it will create a depression or hollow as the sheet bends around itself. However, a black hole acts as if an extremely heavy and compact object were placed on a piece of paper, creating a well so deep and steep that it forms a sort of funnel. The closer you get to a black hole, the steeper the curvature becomes, and eventually a singularity forms at its center, where the curvature of space-time becomes infinite. This curve has several noticeable effects. For example, light traveling near a black hole follows a curved path because of the strong curvature of space-time. This phenomenon, known as gravitational lensing, can bend, distort, or even multiply images of background stars or galaxies, creating spectacular astronomical observations. Near the event horizon, the boundary beyond which nothing can escape the attraction of a black hole, time appears to slow down when observed from a distance, a consequence of the intense gravitational field. This effect, predicted by Einstein, is known as time dilation and has been confirmed by various experiments and observations. In addition, the escape velocity within the event horizon exceeds the speed of light, making it impossible for ordinary matter and signals to escape once they cross this threshold. In addition, black holes can strongly influence their surroundings by accumulating matter. As matter spirals into the black hole, it forms an accretion disk that heats up to extreme temperatures and emits X-rays and other types of radiation. This process further emphasizes the black hole's ability to bend space-time and energy around it. The curvature of space through black holes provides insight into the nature of gravity and the underlying structure of the universe. These fascinating objects continue to attract the attention of scientists, pushing the boundaries of our understanding and revealing new mysteries of the cosmos. The event horizon of a black hole is one of the most enigmatic boundaries of the universe, shrouded in many mysteries that challenge our understanding of physics. The event horizon is the point beyond which nothing, not even light, can escape the gravitational pull of the singularity at the center of the black hole. This boundary marks the region where our normal understanding of space and time begins to break down. One of the most profound mysteries surrounding the event horizon is what happens to the data about matter falling into a black hole. This mystery, known as the information paradox, arises from an apparent contradiction between the general theory of relativity and quantum mechanics. According to the general theory of relativity, any information about matter that crosses the event horizon is eventually lost in the singularity, where it is thought to shrink into an infinitesimal point. However, quantum mechanics, which governs the microcosmic world, dictates that information must persist. The clash between these two fundamental principles of physics has led to various theories and debates, most notably related to Stephen Hawking's proposal of Hawking radiation. Hawking suggested that black holes could emit radiation due to quantum effects near the event horizon, gradually evaporating over time and potentially allowing information to return to the universe in some scrambled form. This idea has sparked countless debates and remains an active area of research. Another significant mystery involves the exact nature of the singularity that lies within the event horizon. A singularity is the point at which gravitational forces become infinite, and the curvature of space-time reaches an extreme. Our current laws of physics, particularly the general theory of relativity, cannot adequately describe the conditions at the singularity. This has prompted scientists to explore theories of quantum gravity, such as string theory and loop quantum gravity, in hopes of developing a unified framework that can reconcile the discrepancies between quantum mechanics and general relativity. Their goal is to uncover the true nature of the cause of black holes and the ultimate fate of trapped matter and energy. The event horizon also raises questions about the observable effects experienced by an object approaching it. From the perspective of a distant observer, an object falling into a black hole appears to slow down and become increasingly red as it approaches the event horizon due to extreme gravitational time dilation. However, from the perspective of the object itself, it will cross the event horizon without experiencing any abrupt changes as it heads toward the singularity. This paradox of perspectives emphasizes the complex and counterintuitive nature of relativity in the field of intense gravitational fields. The black hole event horizon serves as a boundary where our understanding of the universe is put to the test, posing profound and tantalizing riddles about the fundamental nature of matter, energy, space, and time. These unresolved questions continue to inspire theorists and observers alike, stimulating the search for new physics that could illuminate the darkest corners of the cosmos. Current theories suggest that inside a black hole is a realm of extreme phenomena, where our traditional understanding of physics bends and possibly breaks down. The journey to understanding what happens inside a black hole begins with the event horizon, a limit beyond which it is impossible to go. When an object crosses this threshold, it is inevitably attracted to the core of the black hole and experiences conditions different from those of the observable universe. When a person falls into a black hole, their feelings differ depending on the size of the black hole. For a stellar mass black hole, the gravitational forces at the event horizon are extremely strong, causing a phenomenon known as spaghettification. This is due to the steep gradient of gravitational attraction between the head and feet of the object or person, stretching it into a long, thin shape as it approaches the singularity. Unlike a supermassive black hole, which has a mass several million to billions of times that of the Sun, the tidal forces at the event horizon are not as strong, allowing one to cross the boundary without immediate spaghettification. But this relative calm does not last long as one progresses deeper toward the center. At the core of the black hole is a singularity, a point where the density explodes to infinity and the curvature of spacetime becomes infinite. According to the general theory of relativity, all matter and information falling into a black hole inevitably collapses into this infinitesimal point where gravitational forces are immeasurable. However, this image faces the limitations of the general theory of relativity, prompting numerous theoretical physicists to search for a unifying theory that incorporates quantum mechanics, often referred to as quantum gravity. Competing theories, such as string theory or loop quantum gravity, attempt to describe the singularity in terms of quantum mechanics, potentially replacing the singularity with a more comprehensible structural core. In addition to this internal dynamic, another perplexing issue is the fate of information that crosses the event horizon. This leads to what is known as the information paradox. Quantum mechanics argues that information is never lost, while the classical view of black holes suggests that it is irretrievably destroyed inside the singularity. To reconcile these differences, Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation could lead to the gradual evaporation of black holes on cosmic timescales, suggesting that information could be propagated back into the universe, albeit in a highly modified state. This hypothesis is still the subject of intense debate and research, seeking to unify these apparent contradictions between quantum mechanics and the general theory of relativity. Although our understanding of what happens inside a black hole remains incomplete and purely theoretical, existing models present it as a stage for unusual gravitational phenomena and extraordinary quantum effects. As research progresses, we may get closer to unraveling these mysteries and discover new areas of physics beyond our current scientific boundaries. Black holes consume matter and energy from their surroundings through the process of accretion, a gravitational mechanism that can turn seemingly empty space into a region of intense activity and light. The accretion process plays a crucial role in the growth and evolution of black holes, allowing them to gain mass from nearby stars, gas, and even light. When matter such as gas, dust, or stars gets too close to a black hole, it becomes trapped in the black hole's extreme gravitational pull. Rather than plunging directly into the black hole, this material often forms an accretion disk, a spinning disk of matter that spirals into a spiral. Matter in the disk experiences friction and compression, heating to extremely high temperatures, sometimes reaching millions of degrees. This superheated material emits various forms of radiation, especially in the X-ray spectrum, which allows astronomers to detect and study black holes, even though black holes themselves do not emit any light. The intense gravitational gradient near a black hole causes the falling matter to lose angular momentum and energy, gradually spiraling closer to the event horizon. When matter approaches the event horizon, the the relativistic effects become significant. The radiation emitted by this region is subject to gravitational redshift, in which light is stretched into longer wavelengths, a phenomenon predicted by Einstein's general theory of relativity. This redshift serves as a powerful observational tool, providing clues about the behavior of matter in extreme gravitational fields. In addition to absorbing matter from their immediate neighborhood, black holes in binary systems can suck matter directly from the companion star. This happens when the star fills its Roche petal, allowing matter to flow through the inner Lagrangian point to the black hole, forming an accretion flow. This flow feeds the accretion disk, resulting in enhanced radiation and energy bursts detectable at great distances. This process is not entirely efficient, and some of the accretion material is ejected from the neighborhood of the black hole in the form of powerful jets and winds. Such jets, often observed in supermassive black holes at the centers of galaxies, can eject matter at speeds approaching the speed of light and spread out over thousands or even millions of light years. This phenomenon, known as relativistic jet ejection, demonstrates the extraordinary power of black holes and their ability to influence the cosmic environment. The resulting feedback, in which the jets interact with the galaxy and intergalactic medium, may play an important role in regulating the formation and evolution of galaxies. Black holes consume matter and energy through gravitational accretion processes, forming high-energy disks and jets. These mechanisms allow them to grow and exert a significant influence on their surroundings, transforming them, in particular through high-energy radiation and powerful relativistic jets. Despite their strong gravitational pull, these processes allow black holes to extend beyond their invisible nature, opening a window into the extreme physical conditions near their event horizons. The supermassive black holes at the centers of most galaxies, including our Milky Way, are among the most intriguing and mysterious objects in the universe. Despite significant advances in astronomy and astrophysics, these colossal formations are still surrounded by many mysteries, from their origin to their role in galactic evolution. One of the deepest mysteries is how supermassive black holes form and grow to their enormous size, millions and billions of times the mass of our Sun. Two leading theories attempt to explain their origin. According to one theory, supermassive black holes formed as a direct result of the collapse of massive gas clouds in the early universe, bypassing the intermediate stages of star formation. Another theory suggests that they grew from smaller black holes that may have emerged from massive stars or earlier generation star clusters, accumulating mass through accretion of gas, dust, and mergers with other black holes. However, no theory fully explains the presence of supermassive black holes in the very early universe, which is observed to have existed only a few 100 million years after the Big Bang. Another deep mystery is the relationship between supermassive black holes and their parent galaxies. Observations have shown a strong correlation between the mass of a supermassive black hole and properties of the galactic bulge, such as the velocity dispersion of stars. This empirical relationship, known as the M-sigma relation, suggests that black holes and the galaxies they reside in co-evolved together. However, the mechanisms of this co-evolution are still unclear. Supermassive black holes significantly affect their environment, mainly through energetic feedback processes involving jets and radiation emitted by accretion disks. These processes can suppress or induce star formation, regulate gas distribution, and shape galactic structures. A detailed understanding of these feedback mechanisms is necessary to provide a holistic picture of galaxy formation and evolution. In addition, the nature of accretion processes near supermassive black holes continues to be challenging to our understanding. The physics governing the behavior of matter, in the extreme gravitational and electromagnetic conditions near black holes, including how some matter forms relativistic jets, remains a topic of active theoretical and observational research. Instruments such as the Event Horizon Telescope, which in 2019 obtained the first direct image of a black hole's event horizon, are crucial to study these extreme conditions and shed light on the complex dynamics. Supermassive black holes also raise questions about the ultimate fate of galaxies. It is expected that when galaxies merge, their central black holes form twins and then merge into one more massive black hole. The detection of gravitational waves from such accretions, detected by LIGO and Virgo, will begin to provide information about these cosmic events. However, direct observation and detailed understanding of the intermediate stages of black hole mergers provide fertile ground for future discoveries. While we have made tremendous progress in observing and understanding supermassive black holes, many mysteries remain. From the formation and growth of supermassive black holes, to their complex relationships with their host galaxies, to the dynamics of accretion and feedback processes, these questions continue to be among the most exciting in modern astrophysics. Current and future observations, combined with sophisticated theoretical models, promise to deepen our understanding of these colossal enigmas and their role in shaping the universe. Black holes, by their nature, do not emit light, and therefore cannot be observed directly. However, scientists have developed clever methods to study these mysterious objects indirectly, relying on their interactions with surrounding matter and the gravitational effects they have on nearby objects. One of the most effective ways to observe black holes is to study the X-ray emission from their accretion disks. When matter from a companion star, interstellar gas, or other sources is attracted to a black hole, it forms a swirling accretion disk. As matter spirals into a spiral, it heats up due to friction and compression, reaching temperatures of millions of degrees. Before crossing the event horizon, hot matter emits X-rays. Space telescopes such as NASA's Chandra X-ray Observatory, ESA's XMM Newton, and now the James Webb Space Telescope provide detailed observations of these high-energy emissions, revealing the presence and properties of black holes. Another crucial method is to observe the gravitational influence of black holes on nearby stars and gas clouds. For example, astronomers can track the orbits of stars near the center of our galaxy, where the supermassive black hole Sagittarius A is located. By meticulously measuring the orbits of stars, scientists can determine the mass and location of the black hole, which exerts the gravitational force needed to control such orbits. This technique helped provide strong evidence for the existence of the Sagittarius A, for which Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics in 2020. In addition, gravitational lensing provides another indirect method of studying black holes. When a black hole passes between a distant light source, such as a star or galaxy, and an observer on Earth, its enormous gravitational field bends space-time around it, bending and magnifying the light from the background object. The lensing effect can create multiple images or distortions of a light source, by analyzing which scientists can obtain information about the mass and properties of the black hole. More recently, the detection of gravitational waves has opened a new avenue for studying black holes. Gravitational waves, predicted by Einstein's general theory of relativity, and first detected by the LIGO and Virgo observatories in 2015, are ripples in space-time resulting from the acceleration of massive objects, such as merging black holes. The wave patterns recorded by these observatories provide insight into the masses and spins of merging black holes, allowing us a direct look at black hole interactions. In addition, the Event Horizon Telescope, represents a revolutionary advance in visualizing the event horizon. the boundary beyond which nothing can escape the gravitational pull of a black hole. In 2019, the EHT collaboration released the first-ever image of the shadow of a black hole in the galaxy M87. This achievement relied on a global network of radio telescopes working in unison to model a planet-sized observatory capable of resolving fine details in the neighborhood of a black hole. By analyzing the bending of light and radiation near the event horizon, scientists can test the predictions of the general theory of relativity and gain a deeper understanding of the nature of black holes. Although direct observation of black holes is impossible due to their light-absorbing nature, scientists have developed many indirect methods to study them. By studying X-ray emission, stellar dynamics, gravitational lensing effects, gravitational wave signals, and direct images of event horizons, researchers will be able to uncover the properties and behavior of these elusive cosmic giants, enriching our understanding of the universe. Hawking radiation, proposed by eminent physicist Stephen Hawking in 1974, is a theoretical prediction that bridges the realms of quantum mechanics and general relativity theory by suggesting that black holes are not completely black, but emit radiation. This groundbreaking concept has profound implications for our understanding of black holes and the fundamental principles of physics. Hawking radiation arises from features of quantum field theory in the context of curved spacetime around a black hole. According to quantum mechanics, even in the vacuum of space, particle-antiparticle pairs are constantly arising and disappearing. Near the event horizon of a black hole, an intense gravitational field can separate these pairs. In some cases, one particle enters a black hole and its counterpart flies off into space. The escaping particle appears as radiation emitted by the black hole. To an outside observer, this phenomenon results in a gradual decrease in the mass and energy of the black hole over time, which could theoretically lead to its evaporation. The importance of Hawking radiation in the study of black holes is multifaceted. First, he introduces the idea of finite black hole lifetimes, which challenges the idea of black holes as eternal, unchanging objects. The evaporation process is slow in massive black holes and fast in small ones. This suggests that the primary black holes that formed shortly after the Big Bang may have already completely vaporized, or are in the final stages of decay, leaving behind observable effects that astronomers can detect. This theoretical radiation also gets to the heart of one of the deepest mysteries of modern physics: the paradox of knowledge. According to classical mechanics, all information about matter entering a black hole is lost forever due to the singularity. However, quantum mechanics states that information cannot be annihilated. Hawking radiation suggests that on huge timescales, information can be encoded in the radiation emitted by a black hole, and thus resolves this seeming contradiction. Although the exact mechanism of information conservation remains unclear, the hypothesis has spurred vigorous debate and research aimed at understanding the nature of information conservation in the universe. Moreover, Hawking's radiation bridges the gap between quantum mechanics and general relativity, two pillars of modern physics that typically operate in very different modes. By demonstrating that quantum effects can have macroscopic consequences in the strong gravitational fields of a black hole, Hawking's theory provides a key insight into the search for a unified theory of quantum gravity. Such a theory would encapsulate all fundamental forces into a single structure, representing the ultimate goal of theoretical physics. Hawking's radiation is not just a theoretical curiosity, but an important cornerstone in our understanding of black holes. It changes the way we think about these cosmic entities, hints at deeper principles governing the universe, and inspires a quest to reconcile the inconsistencies between quantum mechanics and general relativity, opening the door to new realms of discovery in the physics of the cosmos. Black holes, often seen as dark consumers of the cosmos, hold the potential for revolutionary applications in space travel and energy production, although these ideas still remain in the realm of speculative science. The use of black holes, given their extreme gravitational and energetic properties, could radically change our technological capabilities. One intriguing concept of space travel involves the use of rotating, or Kerr black holes as cosmic shortcuts through space-time. According to solutions to Einstein's field equations, a rotating black hole may possess a region known as the ergosphere, in which space-time is dragged at high speed. Some theories, primarily related to hypothetical constructs like wormholes, suggest that Kerr black holes can form gateways between distant points in space and time. If passable wormholes exist, they could allow spacecraft to travel vast cosmic distances instantaneously, entering at one end of the wormhole and exiting elsewhere in the universe. Such a mechanism, although currently beyond our technological capabilities and perhaps speculative, stimulates imagination about future possibilities. Developing technology that can navigate and withstand the intense gravitational and tidal forces near a black hole remains a challenge. On the other hand, extracting energy from black holes seems a more reasonable possibility, utilizing phenomena such as the Penrose process and Hawking radiation. Theorized by physicist Roger Penrose, the Penrose process provides a method of removing energy from the ergosphere of a rotating black hole. In this case, an object or particle entering the ergosphere can split into two parts, one of which is absorbed by the black hole and the other escapes from it. The remote part could have energy harvested from the rotational energy of the black hole. Theoretically, the energy collected could be utilized for many purposes, potentially making it an incredibly efficient energy source. In addition, theoretical studies of Hawking radiation suggest another way to extract energy. As black holes are slowly vaporized by Hawking radiation, they emit energy-carrying particles. Capturing this radiation could hypothetically provide a constant flow of energy. A more extreme idea is to create microscopic black holes that would vaporize much faster and emit powerful bursts of energy. Some proposed scenarios utilize particle gas pedals or other advanced technologies to deliberately create such micro-black holes and produce energy. However, significant technological and safety hurdles must be overcome to realize these ideas. In addition, black holes could theoretically power interstellar propulsion systems. One speculative idea involves using a black hole as an energy source for the propulsion of a black hole bomb. This would involve placing the black hole inside a massive reflective shell that could amplify the energy extracted from the black hole's rotational energy, creating a powerful propulsion thrust. Science fiction also considers concepts such as a black hole starship that utilizes steerable black holes as energy sources to propel spacecraft at relativistic speeds. Although these ideas are currently in the realm of theoretical speculation, continued progress in our understanding of quantum mechanics, general relativity theory, and particle physics may bring some of these concepts closer to reality. Harnessing the energy of black holes could revolutionize our energy systems and propel humanity into an era of interstellar exploration, demonstrating the potential of these mysterious space objects to unlock extraordinary new possibilities in energy and space travel. Recent discoveries involving black hole mergers have greatly expanded our understanding of the universe in ways we never imagined. One of the most exciting discoveries was made when the LIGO and Virgo observatories detected gravitational waves, subtle ripples in the fabric of space-time that arise when black holes collide. These events, which often involve black holes several times the mass of our Sun, release unfathomable amounts of energy equivalent to several solar masses, which are converted directly into gravitational waves. Accurate detection allows scientists to confirm the existence of intermediate mass black holes, which fill the long-standing gap between small, stellar mass black holes, and the supermassive ones found at the centers of galaxies. Equally exciting are the broader implications for our understanding of the cosmos. Black hole mergers serve as natural laboratories for testing Einstein's general theory of relativity under extreme conditions. The recent discoveries hint that these mergers do not always result in a perfect ring dipping or settling of the newly formed black hole, suggesting that there is more exotic physics at play. In addition, these events are key to unlocking the mystery of heavy element formation. Intense gravitational interaction and the resulting high-energy phenomena have been proposed as sites where elements heavier than iron can form, which cannot be fully explained by stellar nucleosynthesis alone. Continued observation and analysis of such cosmic phenomena may uncover answers to some of the deepest mysteries of the universe and change our understanding of its structure.